mathematicians. Today we see a nice real analysis problem asked in CSIR December 2014. It is a part C problem. It is about homeomorphisms between metric spaces. Okay, let X be a metric space and f from X to R be a continuous function. Then they are defining a set G. G consists of ordered pairs, set of all x comma f of x such that x belongs to x. Okay, this is called the graph of f. Given such a set G, then they are asking whether this graph of f is homeomorphic to x, whether it is homeomorphic to R, whether it is homeomorphic to x cross R, whether it is homeomorphic to R cross x. Okay. Now, if you can make a few immediate observations, then this problem is very immediate. Okay. So, what to do? So if you are new to my channel, please click the subscribe button, and if you are like my teaching, please click the like button in the video. Okay, let's continue this problem. So it is given that X is any metric space. Okay, so the examples of metric space we have seen are like R with usual metric, C with usual metrics, then discrete metric, R2 with usual metric. We have seen examples of such metric spaces, but the discrete metric is a very important one. Why? Because you can take any non-empty set A, then you can define the discrete metric in the non-empty set A. How do you define discrete metric in the set A? Distance between x comma y equal, maybe I'll write it. So distance between x comma y equal to 1 if x not equal to y, 0 if x equal to y. So the advantage of this metric is, the discrete metric is, you can make any set. What doesn't matter what are the elements, you can make any set into a metric space. In particular, you can make a finite set. You take any finite set also into a metric space. Okay, so we're going to make use of discrete metric space in this problem. So we take x to be a finite set. Okay, and with the discrete metric, and we're going to see how the set G looks like. Using that observation, we can eliminate option and we prove the correct option theoretically. Okay, so let's see. So consider x equal to singleton 0. Like singleton, it is a one element set. As I said above, we can make this single element set into a metric space by defining discrete metric in this set. Okay, now let us consider a continuous function from this metric space into R. Let f from close 0 singleton 0 to R be a continuous function. Here let's make a remark. I'll make a remark here. If you have so if you look at a function f from A to some metric space M, okay, if this domain has discrete metric, then every function will be continuous. Okay, that is because if you look at this metric, in this metric all the subsets of A will be open. Therefore, inverse image of open set will be open for every set, every function f. Okay, so if the domain is discrete, domain has discrete metric, then every function will be continuous. So now here we are looking at a singleton 0 with a discrete metric. So every function will be continuous. So in particular, I take one such function f from singleton 0 to R be a continuous function. Then we look at the set G. Okay. If you look at the set G, it contains set of all x comma f of x such that x belongs to x. Okay, so for each x in x, you have a point x comma f of x in the set G. Okay, so here there should be a bracket. They missed it. Fine. So there is a bijection between the set x and G because for each x you have a point x comma f of x. So that will give you a bijection, like x goes to x comma f of x. Conversely, x comma f of x goes to x. This is an inverse function. Okay, so this gives a bijection between x and G. Now, if we assume x is a finite set with some metric, for example discrete metric, then G will have finite number of elements. Okay, so if G has finite number of elements, then we can eliminate the option easily because homeomorphism, like suppose M1 and M2 are two metric spaces, we say that M1 and M2 are homeomorphic if you should have continuous function, you should have a continuous function f from m1 to m2 and its inverse f inverse also should be a continuous function from m2 to m1. Okay, so basically m1 and m2 are homeomorphic if there exists a bijection f from m1 to m2 such that f is continuous as a function from m1 to m2 and its inverse is also continuous as a function from m2 to m1. Okay, so if m1 and m2 are homeomorphic, you need a bijection between them. Okay, so two metric spaces are homeomorphic, at least they should have the same number of elements. Okay, so here if x is a finite set, finite metric space, then G will also have finite number of elements. So in the second option they are saying that G is homeomorphic to R, but if you take X to be a finite metric space, G will have finite number of elements, so it cannot be homeomorphic to R. Similarly, cannot be homeomorphic to X cross R because R, X cross R cross X, all these sets has cardinality uncountable. But we can, by choosing X to be a finite metric space, we will have G is a finite set. Okay, so all these G's are finite set. R, X cross R cross X are uncountable set, so there cannot be any bijection between them. Therefore, they cannot be homeomorphic also. So options 2, 3, 4 all wrong. We just need to verify the first option. Okay. So for example, in this example, so we take X to be singleton 0 and we take a continuous function f from singleton 0 to R. So this function's image is, you just need to define the image only on 0, right? Therefore, the graph of the function consists of only one point, 0 comma f of 0. Okay, so G is a singleton set because X is a singleton set. So I said X and G are in bijection. So here it has only one element. So G also has only one element. Therefore, so now G has only one element. So like therefore one singleton set cannot be homeomorphic to R. Cannot be homeomorphic to X cross R. Cannot be homeomorphic to R cross X. That is a particular case of what I said. Okay, let's continue. So now we claim that so we have eliminated these options. We claim that G is homeomorphic to X. Okay, how to prove that G is homeomorphic to X? So we claim that G is homeomorphic to X. So what we have a continuous function from X to R, and we define G is the graph of the function f. We claim that this graph of the function f and this X metric space X is homeomorphic. Okay. So to prove G and X are homeomorphic, we need a bijection f from G to X such that f is continuous and f inverse also continuous. So let's see how to do. So we already used f. So we define a function phi from G to X such that phi is continuous and phi inverse is also continuous. Let's see. So we define a function phi from G to X by pi of x comma f of x goes to x. Note that every element of G is of the form x comma f of x. So we define element phi on x comma f of x, and the image is this x. Okay, so note that x belongs to x. So this function is well defined function from G to x. So we claim that this is a continuous function. If you know some topology, it is easy to see that this function is continuous because this is projection onto first coordinate. Okay. Now G is a metric space, X is a metric space, R is a metric space. So their product is also a metric space in the product topology. Now G is a subset of X cross R. Okay, so we have to visualize G with respect to product topology only. Okay, so now G has product topology. Whenever you have product topology, the projections are continuous. Okay, therefore this is a projection onto first coordinate. Therefore, our function phi will be continuous. Okay, if that is one argument, or otherwise you can take a sequence in you can use a sequence criterion also. Okay, you take a sequence that converges to a point x comma f of x, So if xn comma f of x converges to x comma f of x, then pi of xn comma f of x and converges to pi of x comma f of x. Therefore, pi is continuous. Okay, that is another sequence argument. Note that sequences in G are of the form xn comma f of x. Okay, so so basically phi is projection under first coordinate. Therefore, it is continuous. That is easy to understand. Now we want, so phi is a function, it is continuous. We claim that phi inverse also continuous. For that reason, we define a new function tau from x to g defined by tau of x equal to x comma f of x. Okay. So again, we claim that tau is continuous. How do we prove? So we take x and tend to x. We claim that f of x and converges to. Actually, we should write. We claim that tau of x and converges to tau of x. Okay. I think what I wrote was correct there. Okay, so suppose xn converges to x in x. Okay, we claim that tau of xn converges to tau of x to prove tau is continuous. Now, since xn tend to x and f is a continuous function from x, continuous function from x to r, f of xn converges to f of x. Okay, so now we have xn converges to x and f of xn converges to f of x, means that x, the sequence xn comma f of xn converges to x comma f of x. Okay, whenever you have two coordinate sequences, their convergence means that first coordinate converges to first coordinate, second coordinate converges to second coordinate. Okay, therefore if xn converges to x, then xn comma f of xn converges to x comma f of x. This is because f is continuous. Therefore, this is nothing but tau of x and this is nothing but tau of x by the definition of tau. Therefore, in x, whenever xn tend to x, tau of xn converges to tau of x. Therefore, tau is a continuous function. Now, if phi is a continuous function from g to x and tau is a continuous function from x to g, we claim that they are inverses of each other. So, now tau composition phi is a function from g to g. Okay, because phi is a function from g to x, then tau is a function from x to g. When you compose them, first you apply g, then you apply tau. Okay, so g to x to g. So finally, it is a function from g to g. So now tau composition g. So if you take a point in g, it will be of the form x comma f of x. Tau composition phi of x comma f of x is equal to tau of pi of x comma f of x. Phi of x comma f of x equal to x by the definition of phi. Now tau of x equal to x comma f of x. Okay. Therefore, tau composition pi of x comma f of x equal to x comma f of x. Okay. Therefore, we get tau composition phi is the identity function. Similarly, you can prove pi composition tau also identity. Therefore, these functions are inverses of each other. So, inverses exist only when the functions are bijection. Therefore, phi and tau are bijections. Okay, they are already, we proved that they are continuous function. Therefore, there is a continuous function from x to g whose inverse is also continuous. Therefore, g is homeomorphic to x. Okay. Okay guys, if you learned something new from this video, please click the like button and share with your friends and subscribe to my channel. Thank you.